I'm Toby Flynn. I'm going to be talking about Gr-EnOcean. It's a new out-of-tree module for a commercial IOT protocol. Why did I choose this particular protocol to look into? So Gr-EnOcean is a developing commercial IoT standard, which is different than a lot of the other ones. It's designed specifically for low power type of platforms, like solar paneled IoT sensors that you would put up in a commercial building. I was actually in a hotel recently that had these types of sensors throughout the hotel, measuring its carbon dioxide and various air quality things throughout the hotel. So that's what it's designed for. They have a lot of variety of sensors. They have contact sensors, temperature, pressure, CO2, occupancy, but it's aimed at a commercial market. And they actually sell a developer kit, which I bought, that allows you to plug into a Aruba network and backhaul it all through Wi-Fi. So it's a developing standard, but it's different than your normal LoRa type standards. The other thing is, the nice thing is it's kind of a commercially available and open standard. All the documents for it are available publicly. You don't have to log in or create NDAs. And then, from a security standpoint, they're adding security into this. Like I said, I found it unsecured in a hotel. Having a file layer implementation in Gnu Radio could be fun to play with. And more importantly, I felt like it would be a fun thing to do. And I was just looking for something fun. So for the actual protocol, there are two basic protocols. There's the original one, which is simple ASK or OOK. And then they have a 120 kilohertz FSK. And I've only implemented the FSK because I can't find any ASKs. They were all only sold in Europe, and they have now moved on to their new standards, so you can't hardly find any of the old devices from that aspect. So what does it look like? Like I said, it's just a simple FSK, 62.5 kilohertz offset for the frequency deviation, 125 kilobits per second, with a lot of tolerances and various other standards. That's all part of the spec, which you can go find. It's the Gr-EnOcean Radio Protocol 2 document. So what does this look like when we're actually talking over the air FSK for these types of sensors? It's just the typical, give it a second. There we go. So like I said, it's 62.5 kilohertz offset, which is something else just hit us. But what you get for being in ISM bands. But those two peaks that we had up were 62.5 kilohertz deviation, which is what you saw from the spec as far as the FSK is concerned. That's what you were expecting to see. Now for the frame structure, since that is just a straight up FSK. I originally thought this was going to be very complicated when I first started looking at the spec, then it turns out to be, no, it really is just a simple FSK. It does have a preamble, which is all ones and zeros, and then there's a sync word attached to it, and if you put it together, it's actually pretty good for locating it. So, first thing I was doing was just playing with it. running it through just a simple quad demod to get out the bits, just for proof that I could actually find sort of where the signal's at. And if we go through and look, there's your 1 0, 1 0, 1 0, 1 0, a couple of zeros at the end, the double ones, just like the synchronous pre-word. Yeah. Still, you're missing parts, right? This is for a full up demod. You need all the GSM, Gaussian sync word. You need to have some other things put into it. From the wonderful tutorials that Barry has written, we have a nice documentation in the radio block, kind of shows you how to do all this stuff and set it all up. Oh, shucks. Somebody already transmitted on me. So here, what we've done, or what I've done, is basically set it up with a correlate access tag, which is looking for the preamble that we'd mentioned earlier. And then it's just tagging it and sticking it in. The hardest thing for this is coming up with a sensitivity block for the GFSK, which is straight out of the documentation for the FSK modulation. And it ends up being pi over 2 times samples per second. Which is documented in the code as all places, but you know, it is nicely documented right here. A little bit different than what the documentation says, but the code was, because the documentation has it defaulting to a 1 for the Gaussian, you need to do this. So this is where the first custom block came into play. Basically, this is a tag header to PDU. The spec that we have back here in the documentation specifies that the header length is, the length of the entire packet is specified here. To give you an idea of these packets, roughly, most of the ones we're seeing are only 9 bytes long, which is 0.7 milliseconds of on-air time. So there's some of the bytes coming out of this particular sensor. Well, I actually have multiple sensors up here that are sending different bytes through, and you can see in the lower debug, from the debug printout, this is bytes. The last one here is a CRC check. We've passed all of that. We've checked the CRC at this point, and we're verifying everything. And then from here, that was the end of the spec that associates with all the radio frame. Then they have a gigantic spec for the serial interface to these modules, and they actually have a dongle that you can attach to a computer that will interface with with all these sensors. There's some nice Python software that's available on GitHub that interfaces to the dongle. As you can see, there's been some temperature values. So from one of the temperature sensors that's sitting up here, it's 20 degrees Celsius. or so it thinks, but here was another one who thought it was 30. I'm not going to tell you that the sensors are great. I'm just telling you what they're reading. And this is based on the dongle and this thing's from. So multiple sensors, it's either 22, 20, 30 degrees Celsius, something like that in here. So from the packets that we saw a minute ago, you'll notice that these all start with like A5 and 06A. But the packets that we found all started with 0A. So what it really is there's a header in here, but when they go, and then the 220412dB is the ID of the device sending it. When they come over to the serial LAN, they stick those toward the back. They don't leave them in the front anymore. So they're moving all the data around, they're shifting everything, and it's a very complex serial. And the interface to the serial, to the debugger, has to be put into the serial format that comes out. So, the spec is available out there. It's on the Gr-EnOcean serial website. And the radio packet format has to be modified. So on this one, you're starting to see now the complete packet. This is matching the USB dongle entirely, but we have a nice file layer implementation, all in GNU Radio. And what ended up happening was we ended up using basically 2 out-of-tree blocks, and everything else in here are just straight up GNU Radio blocks. They needed no modifications. All we had to do was do a little bit of tweaking on the frequency FSK sensitivity. Correlate access block was needed nothing changed to it. One thing to remember, through the documentation it tells you, but the access code pulls the header out when it finds things. I'm hoping one of these other sensors will talk here in a minute. So you can see what the radio actually sees is here, and then in this case it was one of the temperature sensors came through, and there's your 20.39 degrees Celsius that we were seeing with the dongle, and it's also showing up over here in the dongle. And of course, it crashes. It's all good and so what fun is it if you can't go ahead and try the transmit side? So we went ahead and I made a very simple block that all it's doing is replaying some various radio packets that I have found. I haven't tried to reverse the serial, didn't turn it back into those radio packets because that was already complicated enough to go the other way. But, if you're wanting to do fuzzing attacks, once again, this is just straight up GNU Radio blocks. The only exception is, once again, the sensitivity, getting it correct with the samples and the frequency deviation being functions of it. So I've got a little demo set up. Had the demo set up. Working. As all good live demos go. No, it's not. This particular one is sending out a GNOME packet. Which is the one that's ending in the 143 for the raw value on it, 17 degrees Celsius. It's a hard coded one. I happen to know what it is, so I can find it. I'm receiving it with the Gr-EnOcean USB dongle that is their radio interface, so proof that we are actually transmitting it live to the dongle and it is receiving it. So we have a way of doing a replay attack if we choose to do this. Or you can customize it. You can go in and play with the bits. It's a very simple Python replay block that it is just the actual bit values. So it would be fun to play fuzzing attacks. I just haven't had time to do it to see what happens when you do it. I know we can crash the, I have crashed the Python IOT serial debugger a lot playing with that. But I don't know how it actually affects the full system until I put it into something where you have the whole service going back through the Aruba network. But I do know that it will crash out of the open source code, which doesn't really mean much more than it crashes the open source code. And the code is available on GitHub. And does anybody have any questions?
I see no questions from the room, but I have two. One, is this part of the CTF? If not, when will it be part of the CTF?
Not part of the CTF? Up to the CTF organizer? It very well could be. Come see me. I will happily help with anything y'all need to make it part of the CTF.
Excellent. And just any advice for people looking to implement new out-of-tree modules to stand up new protocol support for the next weird RF thing that they come across?
The tutorials are very good, even for someone who's been in GNU Radio for a long time. I highly recommend using them. Also, it is open source. Use the source code. Leverage other people's blocks by all means. That's what the whole point of open source is. Sometimes the blocks, like, I had to write a couple of out-of-tree modules for very specific processing for that. But there's good examples, and I intentionally made one of our out-of-tree blocks is C++, the other one is Python. I have the message passing back and forth through all of that. Actually, is more of a test or a proof, but so we already knew GNU Radio did it, but it's more examples out there of both Python and C++, message passing, handling, going back and forth, streaming, and packet handling.
Thanks. Any other questions? Excellent.
I was just doing a quick Google search on Gr-EnOcean versus LoRa, and I was just wondering if you had any thoughts on the two IoT protocols.
So I have looked at LoRa a lot. I said I have looked at LoRa. It is so Gr-EnOcean is specifically targeted at IoT for commercial infrastructure. So they are setting themselves up, targeting with like Aruba networks to backhaul their stuff. All of their sensors are relatively small. They pretty much all have little solar panels on them. So it's actually designed to be able to put into a room like this and hidden in the infrastructure and get all of its power off of the lights. They can have a battery backup, but it's not required. And they have switches on them where they may only report once every 10 or 15 minutes. LoRa is, like LoRaWAN. So these are all 902, it's FSK, it's 125, it's relatively short range, in all honesty. LoRa, depending upon how you configure it, could be very long range, LoRaWAN, so it's really good for, I think, things where you're wanting more of, trying to think. So LoRa is a fairly open standard if you've ever tried to play with the LoRa sensors. It's all how you put together a module and how you configure it, and it gives you so many options. These options are really fixed, so it's really nice because they have multiple providers. It's almost like LoRaWAN, part of the LoRa network, but it's not really designed to need something out receiving it. A lot of the LoRaWAN has commercial people operating the LoRaWAN receivers. This one's designed that you put it in your own.
Farmer wants to know soil. Farmer wants. Sorry. The LoRa is agricultural type of sensors, like the soil temperature, the barometric pressure, the air temperature, all the things that a farmer would need. And when you had mentioned that yours is based on solar power, just seemed like a fit. So I was just curious if any of the Gr-EnOcean sensors.
Yeah, I just picked Gr-EnOcean because it was fun. Not because I'm not an Gr-EnOcean salesman by any stretch. So I'm not trying to sell you the protocol. It was just fun. It was just, attacking and reversing an IoT for the sake of reversing an IoT standard. I'm not telling you that Gr-EnOcean's good for anything. Yeah, I do SDR, not IoT device manufacturing.
One more question from the internet was, when you were developing this module, did you come across any features that you thought were missing, either in the protocol or in GNU Radio itself?
The thing I had tried to use in GNU Radio that was really hard and led me to doing the custom block was, this is a simple header. The header structure is relatively simple. It has a preamble and a packet length. But trying to get that without writing a custom block to go pull that out and make the packet length based off of that, with the header implementation that's in GNU Radio, it seems like it's very fixed to the header that, like the D header, the header processor is made for the header that GNU Radio automatically puts on something, and trying to figure out how to do that part of it became hard, so I just wrote the custom block. But I did look into I was doing my best to use all standard GNU Radio blocks, but I was having a hard time, and someone else had mentioned earlier too, the packet header processing within GNU Radio is kind of hard to deal with.
Cool, thanks.